Hello, this is Mr. Collier, and today we're looking at the limit of a function. So let's look at this piecewise function first. It looks like this. We have y equals 2x, 4x not equal to 1, so it goes through here. At 1 we would have 2 for the y value, and then it keeps going on like that. So at x equals 1 we have 3 is actually the y value, so we have a jump discontinuity here. Okay, so it's not a continuous function, but it does converge to 2 as x approaches 1. So if you look at going this way, the y values get closer and closer to 2, and going this way, the y values get closer and closer to 2. So the limit does exist even though it's discontinuous here. Okay, so the way we show that is we have the limit as x tends to 1 from the right. We put a little plus sign up there like that, of f of x equals 2. And we have the limit as x tends to 1 from the left of f of x equals 2. Okay? So the limit from the right equals the limit from the left, and they both equal 2 in this case. Okay, let's look at this function, the tan function. So in the tan function, if you recall, it looks like this. Okay, and we have asymptotes at like negative pi over 2, pi over 2, and then we've got same thing happening again up to 3 pi over 2. So recall, we've got these vertical asymptotes because tan is undefined at pi over 2 and 3 pi over 2 and negative pi over 2. But the limit in this case doesn't exist, because if you look at the limit as x tends to pi over 2 from the left, you put a negative up here, of tan x. So as you're coming from the left, it goes off to infinity. And as you go from the right, the function's going off to negative infinity. Okay, and those two limits are different. Okay, so if we find the limit of a function at a point by having the sequence approach from the left, we write, okay, this is what we're just talking about, we write from the left as a negative and from the right as a positive, and only when they're both equal does the limit exist. Let's take a look at another example here. So we got another piecewise function. Show that this function has no limit at x equals 2. So we just have to find the limit as x tends to 2 from the right of f of x, and the limit as x tends to 2 from the left of f of x. Okay, so from the right, we're looking at here x is greater than or equal to 2. Then this function approaches 0. Just plug in 2 and you get 0. Maybe I'll show that. 2 minus 2 equals 0, and here the limit on the left will give you 3 times 2 minus 1, which equals 5. Okay, so you could say since the limit as x tends to 2 from the right of f of x does not equal the limit as x tends to 2 from the left of f of x, then limit as x tends to 2 of f of x does not exist. Okay, next we have another piecewise function. Show that limit as x tends to 0 is 1. Well, we have limit as x tends to 0 from the right of f of x is going to be equal to the limit as x tends to 0 from the right. So 0 is here, so from the right will be this function, x minus 1, which equals 0 minus 1, which equals negative 1. the limit as x tends to 0 from the left of f of x equals limit as x tends to 0 from the left of 1 over x minus 1, which equals 1 over 0 minus 1, which equals negative 1. Okay, so since limit as x tends to 0 from the right of f of x equals limit as x tends to 0 from the left of f of x equals negative 1, then limit as x tends to 0 of f of x equals negative 1. Okay, next we have this limit. We have the limit as x tends to 0 of cosine 1 over x. And there's a method for doing this with subsequences, but that's actually beyond the scope of this course. So I'm just going to show you what the graph looks like for this one. So here's the graph, and you can see that it oscillates, keeps oscillating more and more and more as x tends to 0. So it's almost like the limit is simultaneously 1 and negative 1, and that's what the proof involves, showing that a subsequence converges to 1 and a subsequence converges to negative 1. So the limit does not exist because those two values are not equal. Okay, so the limit of this one does not exist. Does not exist. Okay, next we're going to do this limit, which actually converges to 0 by the squeeze theorem. So let's do cosine 1 over x is between 1 and negative 1. Now, if I look at x cosine 1 over x, it's between then absolute value of x and negative absolute value of x, right? Because x could be positive or negative, so if we take the absolute value of it, then x is between, well, let's write it up here. We know always that x is between absolute value of x and negative absolute value of x, right? Anyway, so we have this, and of course the limit as x tends to 0 of negative absolute value of x equals 0 equals the limit as x tends to 0 of absolute value of x. Therefore, the limit as x tends to 0 of x cosine 1 over x equals 0 by the squeeze theorem. Okay, next we have a few more examples. Now, if possible, when calculating a limit for a simple like polynomial function, you can just plug in the value. Okay, so we can just plug that in and get 3 cubed minus 5 times 3 minus 8, which equals 4. Okay, so in the next example, that doesn't work because you get to divide by 0 here, right? But notice the numerator factors 2x minus 2 times x plus 2. Okay, now we can cancel these out because we know x is never going to be equal to exactly 2, it's just approaching 2. So there's no problem canceling those out. It's the same as the limit as x tends to 2 of x plus 2, which equals 2 plus 2, which equals 4. Okay, the graph would be maybe something like actually it would be a straight line, x plus 2, and then when we get up to the x value of 2, we'd have a hole in it. So it looks like a linear function. Okay, next example, if you plug in negative 2, you get a 0 in the denominator. So that doesn't work. So what we can do actually is we can multiply by the conjugate, but even more helpful is actually completing the square, as you'll see in a second. So this equals the limit as x tends to negative 2 of x plus 2 all squared, and in the denominator, if you complete the square, you get x squared plus x plus 2 squared plus 9 minus 3. And then I'll multiply by the conjugate. You get root x plus 2 squared plus 9 plus 3 over root x plus 2 squared plus 9 plus 3, so that's the conjugate. You'll get limit as x tends to -2 of, in the numerator, we're going to have x plus 2 all squared times root x plus 2 squared plus 9 plus 3, and then the denominator, since we're multiplied by the conjugate, we're just going to get x plus 2 squared plus 9 minus 9. And of course these cancel, and then you can divide and these cancel. So this just equals the limit as x tends to -2 of root x plus 2 squared plus 9 minus 3. And now we have no problem substituting in x equals -2 to calculate the limit. So you do that, and this becomes 0, and we're just going to have root 9 minus 3, which equals 3 minus, so this would be a plus 3, so we get 3 plus 3 equals 6. Now, next example, D here. We're also going to use a squeeze theorem here. So we have sine 1 over x is between 1 and -1. Then we'll do e to the power -½ is less than or equal to e to the power of sine 1 over x less than or equal to e to the power 1. And then we can multiply both sides by x squared because it's positive. X squared e is less than or equal to x squared e to the sine 1 over x is less than or equal to x squared e. And the limit as x tends to 0 of x squared e equals 0. And that's equal to the limit as x tends to 0 of x squared e. Therefore, limit as x tends to 0 of x squared e to the sine 1 over x equals 0 by the squeeze theorem.